so as you can see from our previous lectures, actually the the whole emphasis on most of the specification of first order logic is actually of a very algebraic nature. But historically speaking, of course, what happened was that the inspiration for all this really came from Euclidean geometry. And what Hilbert did, which it will go well beyond this course, but at least it's a good idea to know that it was something that he could do, is that he actually based. So even though it was inspired by geometry and essentially Euclidean geometry, uh, Hilbert based his entire axiomatization of Euclidean geometry on the real numbers, so on the real field. So in that sense, he had already algebraized Euclidean geometry, because the main things in geometry actually were of the form of measurements, right? So measurements of line segments, congruences, measurements of angles, and they were all essentially, so he required the real field on which to base all his axiomatization. So what Hilbert actually did was that he looked closely at Euclid's Euclidean geometry, and found that there were a lot of there were quite a few loopholes, logical loopholes in many of Euclid's statements and proofs. For example, one of the things was that Euclid's proof of the congruence of triangles would typically go as place this triangle on top of the other triangle and just and it was a sort of hand waving proof which said that okay, this vertex coincides with that vertex and this vertex coincides with that, and therefore the two triangles are congruent. I mean, it is a completely hand waving proof. Whereas the whole idea about Euclidean geometry was that it was supposed to be essentially, so what Hilbert got from that kind of proof was that he is essentially saying that Euclidean geometry is invariant under translation, rotation, and possibly even reflection. Yeah, but those invariant properties should not be part of the formalization unless you can prove invariant properties. So the model for Euclidean geometry, which actually comes from coordinate geometry, is not really invariant under translation, rotation, and so on, because the notion of a point in that is a pair of xy coordinates. So when you translate a triangle, you get a different triangle with different vertex points, and it might be congruent, but it is not translation invariant, for example, or rotation invariant. So the emphasis at that point, late in the 19th century and early 20th century, was actually for looking at invariants through homomorphisms and so on and so forth. So what Hilbert actually found was that it is possible to define, in addition to Euclid's axioms and postulates, it's possible to assume the field of real numbers, and actually he had to define some extra axioms and postulates. So the final list in Hilbert's axiomatization of Euclid's geometry was something like 18 axioms, 18 postulates, right? And many of them were derived from the reals, because they had to deal with congruences and measurements and so on and so forth. And besides that, of course, there were these non-algebraic features like parallelism and so on and so forth. And but essentially he could reconstruct the whole of Euclidean geometry rigorously within a first order logic framework with about 18 axioms, and he could actually prove all those theorems. So in particular, one major change that this formalization required was that you had these three congruence of triangles rules, right? The SAS, SSS, and ASA. Hilbert found that you had to assume one of them as an axiom, as a postulate. So if you do not want to go along with Euclid's notion of move this triangle on top of the other triangle and so on and so forth, then one of these three congruence things, actually what Hilbert did was he took the SAS as a postulate and he proved the others essentially through one-to-one correspondences and so on and so forth. So for example, Hilbert's proof of the base angles of an isosceles triangle are equal, right? I mean, so that actually involved, sorry, this looks too much like an equilateral triangle, but let's assume it's just an isosceles triangle, right? So that there were lots of subtle things. One of the standard things that happened was that, so you are given that, you are, for example, given that these two sides are equal, and you have to prove that these two angles are equal. One of the standard things was that you drop some perpendicular or some such thing, or you drop a bisector and then prove that the two triangles are equal. But there is a certain logical flaw in that. How do you know that if I drop, I mean, so the notion of if I drop a perpendicular, for example, then there is no guarantee that it lies between these 2 points. So logically speaking, how do I know that without drawing diagrams, how can I guarantee things like that the perpendicular will drop between these 2 points? So which means the notion of betweenness, the notion of one point lying between other two, these were definitions which had to be made in terms of measurements and so on and so forth. And then you had to give an additive axiom also to say that, well, if there is a point between two different points on a line, then the sum of the measures of the two line segments equals the measure of the larger line segment and all those things. So, so what Hilbert did was he instead used something like one-to-one correspondences. So he actually defined triangle congruence, for example, as a one-to-one correspondence, which should preserve measures. So there are 6 measures, 3 segments and 3 angles, and if all 6 measures are preserved, then the two triangles are congruent. Yeah. So in the case of this, without getting into betweenness and so on and so forth, what he did was he proved that this triangle ABC was congruent to the triangle ACB without dropping perpendiculars or even bisectors. I mean, it's possible that if you had defined betweenness and defined the notion of bisection, you would have got betweenness, and then there's a guarantee that bisectors would lie there. That's another way of proving, but this is an innovative proof using just one-to-one correspondences. So he basically proved that this triangle was congruent to itself with a different correspondence, right? And from which it followed from the definition of congruence that these two angles would be congruent. Yeah. So there were a lot of innovations in what Hilbert did in reformulating geometry, and the other interesting things that he did was, after having reformulated, he showed that his version of geometry was consistent and it was complete. So all the theorems could be proven. I mean, it's an amazingly great result for an essentially an elementary thing. But it takes us too far away from logic for computer science, so we will not get into it. But if you're interested, you should actually look at some of those books of the 1920s, which actually detail Hilbert's axiomatization of geometry. Right. So we will look at other first order theories from a more modern viewpoint. Yeah. So essentially, Euclidean geometry is axiomatizable in first order logic. All of Hilbert's axioms can be proven to be independent of each other, no axiom can be derived from the others, and the axiom system is sound and complete. It's an amazingly complete piece of work that Hilbert did. Okay, so let's get into proof theory, and again we'll follow Hilbert's thing that we want essentially a proof theory of first order logic. What distinguishes now first order logic from propositional logic is the existence of signatures and terms, right? And that's something we have to worry about in quantification. So, if you look at first order logic as a descriptive mechanism, formal descriptive, syntactical descriptive mechanism of a mathematical theory, then firstly we require two kinds of axioms and proof rules. One is the fact that we have got quantifiers means that we require axioms and proof rules for quantifiers, right? So those are the logical axioms and logical proof rules. So in that sense, you've got a two-tier language, so you've got a two-tier proof system. Okay. Then there are the non-logical axioms. These non-logical axioms are what are used nowadays to briefly describe any kind of structure. So you just give the three group axioms and you have defined essentially all groups. So those three group axioms, which by the way have to be what we have done, what we gave as the three group axioms is not exactly the same, because you have to include the existence of unique inverses, and you have to give a universally quantified axiom for that unique inverse. So something like you assume that your signature. Oh, yeah, here we have it. You have the and you have to give this axiom in addition to the associativity, and you have to replace that right inverse axiom by this universal axiom. Yeah, the unique. This is like the unique right inverse axiom. It is clear that you can prove that that left inverses are also unique, and that your right inverse is their left inverse. So it's possible to prove those things, but essentially the group axioms will be those three. Okay. So what we will look at, so you can think of therefore first order logic as a, and since it's a two-tier structure, we'll actually make it a three-tier structure. I'll give the reason for it, but we'll look. So we first of all require logical axioms and rules, and Hilbert had these. Okay. There is a small variation here. Okay, so as usual, I think all of you have to turn around. Okay, so as usual, so I'll call this, since it's first order, I'm calling it H1, and of course it's parameterized on a signature sigma, right? So, and then as we did for propositional logic, we'll assume that there are only three operators, or rather this universal quantifier is actually an infinite set of operators, one for each variable. That's okay. So we'll assume only that there are these two operators and the universal quantifier for all variables. Everything that you did in propositional logic, since predicates are just parameterized propositions, and since the proof system of propositional logic required only pattern matching, right? And logical validity was shown to be pattern dependent, right? In that. So all the patterns which are tautologies in propositional logic can be directly imported into first order logic, right? So, but now when we are talking about patterns, we are talking about exact patterns. So even the variable names should match in the patterns. So in particular, what we are saying is, if I have some predicate of three variables, then this is a tautology where the three variables occur in exactly the same places in both cases. So, for example, you cannot just replace one of these variables, you cannot just exchange these variables and claim that this is a tautology, right. So, if you look at any substitution of terms also, the substitution has to be an exact pattern match, so that when you take three terms S, T and U, let us say, which essentially are substitutions in which the term S replaces X and T replaces Y and U replaces Z, then you have to take exactly the same kind of substitution. So, as the sequence of symbols should also be exactly the same in order to get exact propositional patterns, right. So your tautological, so the tautologies of propositional logic essentially form a skeletal framework of patterns with placeholders which you can import directly into first order logic, right. And therefore, all the tautologies of propositional logic can be imported directly. So, many books instead of saying Ks and N and MP, they just say that take all the tautological structures of propositional logic and think of the atomic propositions there as variables to which you can perform substitution of predicates. Yeah. So, which is why actually I use these new meta-variable symbols like X and Y and so on. So, it satisfies both needs, that of providing skeletal structures and being able to substitute. So, so since of course Ks, N and modus ponens together give me a complete axiomatization for propositional logic, instead of importing all the tautological structures from propositional logic, I just use these three axioms KSN and modus ponens rule. Yeah. So, all propositional structures essentially form frameworks in which I can plug in predicates instead of the proposition, instead of the atomic propositions there. Yeah. So, to each atomic proposition I can think of it as a variable which can be replaced uniformly by a certain predicate, in which the terms also would be identical, identical copies of predicates for every occurrence of the same variable. Yeah. So then every propositional tautology would therefore also be a predicate logic tautology, will be logically valid in predicate logic. The other two, the other axioms and rules of inference are these. One is your universal quantifier essentially means that it does not matter how what term I substitute for a variable which is universally quantified throughout the body of that quantified formula, it is still true. I mean, it preserves truth, it preserves validity, and it preserves satisfiability, right. So the first axiom schema is that for all x in the structure capital X, which might have small x as a free variable, I can replace all occurrences of small x in capital X by any term t, provided, of course, capital X could be a skeletal structure in first order logic, right. So it means it might have other quantifiers, provided no variable of t gets captured by a quantifier in X. So that is what this admissibility is. I think I defined admissibility in some earlier lecture. Basically, you want to avoid capture of free variables, right? Because because free variables have a different meaning altogether in some global context, and they should not be confused with bound variables which have only a local meaning in a local context and by coincidence happen to have the same name. So you should not be able to capture free variables. So in which case, of course, if you you cannot change the variables in T, but what you can do is you can do an alpha conversion by changing the bound variables in X in order to get uh, equivalent predicates, so that it makes T for X admissible in X. Yeah. So one thing is so I did not include this alpha conversion thing, but because that's not something that is there in most books, but it should actually be there. So I should have made it some x prime, where x prime is alpha equivalent to x and T for X is admissible in x prime. That would have been a more accurate way of rendering this axiom schema. Yeah. So this in many cases this is called universal instantiation. But I am following my standard convention of naming, which basically comes from Gensen's natural deduction system, right? And which is inductive on the structure of the formula. So this is just a for all elimination rule. Yeah. It could equally well have been written as this. Yeah, where T for X is admissible. It could have been written as a rule, and in fact in a Gensen natural deduction system it would be written this way. Yeah, but the two things are equivalent, but with a caveat which we will worry about, because the deduction theorem does not exactly go through in predicate logic. There's a problem in the sense that because of the presence of free variables, we have to fine tune the deduction theorem for free variables so that it still continues to hold, and so it holds in a sort of restricted fashion. So then what happens is that these two notions okay, let me write it fresh. So if I have gamma phi, psi is a logical consequence of gamma union phi, and phi arrow psi is a logical consequence of gamma. These two are not equivalent notions. First order logic. And it is precisely because of the fact that there might be free variables hanging around which are not quantified. However, this equivalence does hold for completely closed forms. So which means if you do not have any free variables at all anywhere, then it's equivalent to a proposition, and then the deduction theorem actually holds. Okay, but between the two also there exists some fine tuning which we can do to make, in the presence of free variables, certain restricted variations of the deduction theorem can be made to hold. Yeah, and so we will look at that in some detail in the proof of our deduction theorem. But basically now logical consequence cannot be replaced arbitrarily by an implication. I mean, you cannot move formulae across without first looking at certain restrictions. So that's one thing. So even though these two forms of for all elimination are equivalent, there is some Hilbert found it better to treat it as an axiom so that it remains on the right hand side. There's another one. This essentially says that the universal quantifier can be distributed over the arrow. Yeah. There is a variation of this which actually some people prefer, but I have not found any. There is some books actually prefer this rule, which I'll call for all d prime, yeah, which essentially says that it's an axiom of the form for all x arrow y arrow x arrow for all x y, and then there is a side condition which says that x does not belong to the free variables of x, right? But the point is this: if x does not belong to the free variables of x, then it is possible to actually prove that for all x, x implies x. And actually it is possible to prove this, right? So therefore, I prefer instead of having to have as few side conditions as possible. So I am going with this, which essentially says that I can distribute the universal quantifier across the arrow. But this cannot be a biconditional. Yeah, I mean what I'm saying is there are lots of subtleties of language here. So here, so what we are saying is if this left hand side is valid, then of course I can distribute the universal quantifier this way. But if this right hand side is valid, I cannot necessarily get the left hand side from that. Because in particular, the bound variable x here is restricted in scope to this body x, and the bound variable x here is restricted to the scope of this body y, and they need not be the same. So you may not be able to factor out the universal quantifier easily, but you can distribute it definitely. So the distributive law here works only one way. If you try to distribute it the other way, then you will have to impose various conditions to ensure that somehow you can keep the identity of the bound variable the same in the two, and you have to do enough work to do that, right? So this arrow is strictly unidirectional. You cannot, it's not possible to prove the reverse without putting in a large number of conditions, right? So these rules have to be carefully designed. The other thing is for all I, the Gentzen way of naming would just say that it's for all introduction. But in the case of so what is it? What is the thing? What is the main point here? The main point here is that this substitution at the top, S and this side condition, y does not belong to the free variable of x, essentially says that if I have enough reason, and by enough reason I mean a proof, that by replacing the free variable small x in capital X by any new variable y, the proof still holds, then the proof is independent of that symbol y. Okay? If the proof is independent of that symbol y, then that symbol y can be replaced by any other symbol also. And if it is independent, that means it is also independent of any valuation that y, any value that y might be given in its semantics. And if it is independent of any valuation, then it can be universally generalized. Yeah, I mean this thing is very subtle for reasons that will become clear when we do the corresponding existential rules, and there again we will have to be careful. Okay, but so essentially what this whole thing says is what we actually do in many of our proofs. We say let y be anything of this kind, blah 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 blah, using just the symbol y we do the proof, and then we say therefore it holds for all y, therefore the universally generalized statement also holds, right. That last step is this universal generalization. Okay, it essentially says that I am using the symbol y throughout the proof, but that is because I need something to, it is not actually dependent on the value of y. It could have been any other symbol and the proof would still be correct, and it would still go through. And if that were the case, then I can generalize on y, right. So these are the rules actually, and we will look at some. So you can see that. So one thing with quantifiers is that supposing you have a statement which is quantified to be proven. We'll do a very small example of that. Then we follow in the Hilbert style or even in the Gensen style. Now actually it does not matter whether we talk about Hilbert or Gensen, because Gensen just has 4 rules. Because he uses the existential quantifier also, but we will derive those existential quantifier rules, so he has just the 2 elimination rules and the 2 introduction rules, right. But basically what we are saying is the structure of any proof of a universal statement or of an let's just stick to universal statements. The structure of any proof of a universal statement goes through a quantifier elimination. The first step is let x be any such thing. That is essentially eliminating this quantifier and putting some variable like y, and then going through a proof. And then the last step is having shown that y remains, y is not a free variable of the original statement x, and therefore the proof is independent really of y, therefore it can be generalized. So the last step is an introduction of the quantifier, right. And in any direct proof of a universally quantified statement, now this is the structure that we see. So there is, between this quantifier elimination and quantifier introduction is the scope of the proof. So that subtree is entirely a subtree which has a certain, which is the scope of the free variable y that we introduce as a result of the quantifier elimination. And you can have subtrees within, if you have many quantifiers, nested quantifiers, then you would have nested subtrees with more and more other symbols occurring, and then you will be gradually generalizing. So you take this entire proof tree which has several quantifiers, then what you have are scopes defined by subtrees for each of those individual variables. Yeah. Okay, that is the large scale structure, but of course we have got a basic obligation. We have to prove that Socrates dies, right? So this is right. So here's this, I mean all this, so it has taken 23 lectures to come to this argument, 22 lectures. So let's do this argument and dispose it off. Yeah. But of course what we need to do is take these verbal arguments. Now we have an extra obligation. What we are saying is we gave all this semantics in terms of sigma algebra, blah, blah, blah. I mean, so we can't just ignore all that. Even if it's a verbal argument like this, we have to somehow specify what is the signature that we are considering. That is an obligation which, by the way, no logic book specifies. Okay? They give you this argument, they give you the proof, and then they're done with it. They haven't told you why they went into signatures and structures and substructures and so on and so forth. But I think we need to do it. So essentially what we are saying is that the signature consists of two unary predicates. One, that of being, so there is some set of objects unspecified, but that is not part of the signature, right? That's a carrier, that's a structure in, if you were to take a model, right? But we have to specify the signature because we are using that in our first order logic terms. And basically what we are saying is that there is some unary atomic predicate called human, and there is another atomic predicate called mortal. And whatever motley set of objects you might take as a model, presumably some subset of it has the property of being human, some subset of it presumably has the property of being mortal. Those subsets could be empty also, but given any non-empty set of objects in which these two properties can be defined, in that signature we require the existence of a certain constant. Okay. So the import of this verbal argument is that in that motley structure, it's a non-empty structure, there definitely exists a constant S standing for Socrates, right? And now you are looking at this argument. So this argument, of course, is just, so now these quantificational arguments are not so easy to translate the way we could translate propositional arguments. Now you have to actually look deeper into the semantics of the sentence and then decide what is the exact translation. So for example, all humans are mortal. The only way to really translate it is that given that being human is some atomic predicate, being mortal is another atomic unary predicate. If something is human, for every x it is, if that x is human, then that x is also mortal, right? I mean, so that's, so it actually works out to be a conditional, which is not obvious from the sentence structure, because now the sentence structures go beyond just the prepositions and conjunctions, right? I mean, they go beyond and or so. And of course, the next premise was that Socrates is human, and therefore Socrates is mortal. And the proof is just this. And in this particular case, we are, of course, the conclusion of the proof is about this constant S. So it's not a universally quantified statement, right? So it is sufficient to just eliminate the quantifier. And here when you eliminate the quantifier, I am using quantifier elimination specifically with the constant S. If I did not use the constant S, if I use some Y or Z or some such thing, then I would not be able to apply modus ponens. It's as simple as that, because there is no guarantee. Once a variable is free, supposing I had replaced it by h of z arrow m of z, then the z becomes a free variable of this predicate and z cannot be replaced. Okay. So you have to replace it by this constant S. So in particular, this quantifier elimination allows you to do that, and then you can use modus ponens because now you have got pure propositions. Yeah. And now you are essentially using modus ponens on pure propositions or on pure propositional forms. We'll see another example here. So here let's look at the mortality of Greeks, right? So all humans are mortal, all Greeks are human, therefore all Greeks are mortal. So this is an argument in which you actually have universal quantification everywhere, right? So this, by the way, so what we can do is, so you, now as I said, no, this is a faulty proof. I mean, basically you're using transitivity of the arrow when that arrow is deep inside some tree. You cannot apply rules like that. Why? There is a very simple reason why you cannot apply rules deep inside the abstract syntax trees, because it's quite possible that you make an assumption. Supposing you're doing a proof by contradiction, you make an assumption, and then if you do this application of modus ponens deep inside a tree, then you might actually come up with false conclusions which do not preserve it, because eventually if that assumption led to a contradiction, then you can obviously prove anything, so it does not matter, right? So in any case, in any proof that involves quantification, you cannot apply such rules like the transitivity of arrow directly. You have to, the transitivity of arrow is a propositional rule. It is not a predicate calculus, it's not a predicate logic rule. So if it has to be applied, you have to first get propositions, or at least propositional forms, and only then apply them. Which means that in order to be able to apply this, you have to first eliminate the quantifiers, right? So this is a faulty proof, right? I mean, I have seen this kind of steps in many logic proofs by students, and that's why I brought it in here. This is simply not acceptable. The only time when it's acceptable to go deep inside a tree and replace some subtree by another subtree is when you can prove that those two subtrees are congruent. So if for example, logical equivalence is a congruence relation, right? So then you can actually do that replacement, but that is the only time you can do that. You cannot do that for any other operator, right? Okay, so that's why these simple arguments are important. Here's another faulty proof, right? So here I eliminated this quantifier by using a variable y. I eliminated this quantifier by using a variable z. And then somehow suspiciously I am using a transitivity rule, which is not acceptable, because as proposition, so these are not necessarily propositions, they are propositional forms with variables in them. But as patterns, this h of y is not the same as the pattern h of z, because y and z are different variables, right? And from our semantics of predicate logic, it is clear that under certain valuations y and z might have different values, in which case the truth is not guaranteed to be preserved by your by this kind of an assumption. So so you cannot just arbitrarily substitute variables and prove therefore gy arrow my and do this kind of fudging, right? This is another mistake I have often seen in logic proofs by students. So that's why I thought I'll bring it to light. So you have to, so the only correct the correct way of doing it is to ensure that you use the same symbol, and for both quantifier eliminations, and your quantifier elimination rule allows you to do that, right? So here's a correct proof. I take these two, I choose some variable y, and I use that variable y in both quantifier eliminations. Both of them are universally quantified, so I'm actually free to use the same variable y. And once I have got identical patterns, I'm actually free to use the transitivity of arrow rule to get that gy arrow my, and then I can generalize, right? So this is how first order logic proofs are going to go, and that pattern matching is absolutely important. Yeah, because what you're trying to show, what you're trying to do is that the notion of a syntactic proof, it's syntactic, so pattern matching is essential, and when patterns have to match, they have to match exactly. And by being syntactic, and what we are going to show in our soundness and completeness proofs is that these rules preserve truth, they preserve satisfiability, they preserve validity, right? And they cannot do that if free variables are lying around and are being given arbitrary valuations. Yeah. After all, any propositional form with free variables might have different truth values for different values of the variables. Yeah, so you have to do that. Okay, I said therefore our language is two-tiered, and therefore our proof system is also two-tiered. But there's actually more to it. Our language is algebraic, and in any form of algebra, equality plays a very important role. Okay, but it's not just the equality in an algebraic system, equality relation in an algebraic system that is important. Equality plays other roles also. And the thing is that there are many different flavors of equality. Okay, one is that in the you might have a term representation of something like the natural numbers, for example, right? So what you want to say is that even in the natural numbers, or the integers with successor and predecessor functions, what you're essentially saying is that the predecessor of the successor of any x, for example, is equal to the successor of the predecessor of any x, yeah, of the same x. So you do have identities like this, and these two do not syntactically match. But in any valuation, in any model of the natural, of the integers, for any value of x, the resulting values you get on the two sides are the same. And in that sense, they are equal. So there is a possibility of syntactically different terms having the same meaning, which is what happens when you're asked, which is also what happens when you're asked to write a program. Different people write different programs, but all the programs might be equal in the sense that they give the same input-output relationship. Okay? So there is an equality which comes because of that. The other thing is that it's just that sometimes in a proof by contradiction, for example, proof of uniqueness of something, you must have done a lot of proofs of uniqueness. You assume non-unique. You start with an assumption that there are two different things, so you name them differently. And then essentially you prove that the two names mean the same thing, or they are the same thing. There is that they are identically the same object, right? So there again you have an equality. So even if you did not have, so in fact what I am saying is, actually in many of these cases, even in the case of verbal arguments, what might happen is, for example, what might happen is there might be a quantified formula for all x, for all y something involving x and y, and it's quite possible that this holds only for when x is equal to y, when x and y are the same object. Take the standard case of, let's say, an argument like, okay, I'm formulating the argument on the fly. You read Peanuts comics, right? So nobody other than Charlie Brown loves Charlie Brown, right? Conclusion: there exists at least one X and one Y. There exists at least one X. Okay, wait. Let's formulate it better. Nobody else loves Charlie Brown. Charlie Brown loves someone. Someone loves Charlie Brown. Therefore, Charlie Brown loves himself. Okay, I mean, right? So, if you were to take these as take the quantified predicates, then you will have two bound variables, x and y. And what you are essentially proving is that is true only for the case when x equals y equals Charlie Brown, or at least when it is since it's existential, we are talking about x equals y equals Charlie Brown, but if it is not existential, it might be other things, right? But the point is that you took two distinctly named variables and you essentially prove that they represent the same object, they are names of the same object, in which case those two variables are actually equal. I mean, so you have equality occurring frequently in mathematical proofs, and so even in verbal proofs actually we would require equality. So this thing that it so happened that this argument did not involve equality, but in general if you had lots of verbal arguments, then equality is something that you would have to take as a primitive binary predicate to be used in your first order logic. Yeah, okay. So that is, so equality has a special meaning in all forms of mathematics and logical reasoning, right? And of course we have got various kinds of equivalences. So now, so what we are doing is we introduce a third in between tier in our logical system with axioms for equality, right? Okay, so these are the two axioms for equality. It's amazing. Okay, so there is something here which I'll explain and then we'll stop. Usually any equality or equivalence relation is defined in terms of those three axioms: reflexivity, symmetry, transitivity, and in the case of equality, you're saying that it's also a congruence in an algebraic system, right? I mean, that's so substitutability, right? But actually we require only these two axioms. Okay, so there's a question mark you see here. Okay, so this question mark says that, so this is the substitutability property, which is essentially comes from Euclid, that equals can be substituted everywhere for equals. But the peculiar property of equality is that I am not obliged to, normally when we define substitutions, we define the substitution as taking place uniformly, right? All free occurrences of x will be substituted by t. If you are looking at t for x on some term, you are saying all free occurrences of x will be substituted by t, will be replaced by t. This question mark is essentially to say that you can choose some subset of those occurrences of x and replace them by y. And that is the essential property of equality and congruence. I am not obliged to do a complete uniform substitution. I can just choose to replace some occurrences by equal elements, and I still get something that's equal, right? So this question mark essentially is to denote that x prime is obtained from x by replacing 0 or more occurrences of small x by small y.
the reflexivity rule is equal to.
Oh, I'm sorry, this should be x equals x. I made a mistake. This is a reflexivity rule. So you just require reflexivity and substitutivity, and then next time we'll show how the other properties can be. Oh, by the way, we have to correct this to x equals x. Yeah. So I'll stop here at this moment, and then we'll continue on first order theories.